what we talked about in the first chapter, or chapter 3, I should say. But in this chapter, we're going to look more at some of the protocols like ARP and spanning tree, right? Protecting those protocols. So we're going to look at things like dynamic ARP inspection and some different spanning tree protocol protection mechanisms in this chapter as well. All right. Again, these are protocols that are dynamic in nature, and because they're dynamic in nature, they are vulnerable to attack, right? Now, it's kind of beyond the scope of this class to really talk about the function of spanning tree and the purpose of spanning tree, because that's kind of a long discussion. But in a nutshell, spanning tree is designed to provide us the ability to have redundant links within our layer 2 domain, all right, and to provide these redundant paths within our layer 2 domain without having the deleterious effects of having those loops in our network. So spanning tree is a protocol that's pretty much essential to any layer 2 network. It allows us to have those redundant topologies, but then allows us to effectively disable the links that would cause a loop, which means that frames would be forwarded or flooded through the network over and over and over again, and so on. But because spanning tree is a dynamic protocol, it uses BPDUs to exchange information, and switches process those BPDUs, and they build the spanning tree topology based on those BPDUs. We have to be able to protect spanning tree from different types of attacks. The most common type of attack in spanning tree is to hijack or take over the role of the root in our spanning tree topology. Okay, so we're going to use mechanisms to protect against that. We'll take a look at different spanning tree protection mechanisms and what the goal of those mechanisms are, and so on. Now, PortFast is listed here as one of those tools that provides additional layer 2 security in a spanning tree domain, but the reality is that PortFast is not really a security component, right? In fact, the whole goal of PortFast is to ensure that ports actually come up faster and activate more quickly than they normally would if they were normal spanning tree ports. All right, so as an example, when you plug in a host to a normal spanning tree port, it takes, we have to go through some blocking functions, right? The port goes into a blocking mode initially. If I'm not receiving BPDUs on the port, then I'm going to stay in that blocking mode for about 20 seconds. Then I go through the listening state, then I go through the learning state, and then I go into the forwarding state eventually. So potentially you could have up to 40 or 50 seconds where a port's being blocked before you can actually activate. So PortFast doesn't disable spanning tree on the port. A lot of people believe that PortFast actually disables spanning tree, and it does not disable spanning tree. What PortFast does is it bypasses the spanning tree process. The port goes immediately into a forwarding state once it detects a link. However, on a spanning tree port with PortFast enabled, if the port receives a BPDU, it will become a normal forwarding port, a normal spanning tree port again at that point. Does that make sense? So if I go into my switch, let me go ahead and configure this real quick. If I go into my switch and I configure PortFast, config T interface FA01, the command that I use is spanning tree PortFast on the interface. It gives me a warning and it says PortFast should only be enabled on ports connected to a single host, connecting hubs, concentrators, switches, bridges, etc. to this interface. When PortFast is enabled, can cause temporary bridging loops. The key there is the word temporary. Temporary means that PortFast doesn't disable spanning tree, if the port receives a BPDU, the spanning tree process will start up again, but in the process of that time it takes for us to identify that there's a BPDU to the time that we become a normal spanning tree port, there could potentially be a loop. Okay? So there are a couple of ways that we can implement port fast. We can do it on the interface like I just showed you using the spanning tree port fast command. Or you can go and on the switch and you can implement port fast as a default on the whole switch. So you would use the command, let me get out of interface configuration mode, spanning tree port fast default. Now when you execute the command spanning tree port fast default, that turns on port fast on the entire switch. Is there an exception to that rule? Because you would think that there would have to be, right? There would have to be an exception to that rule, wouldn't there? I don't want port fast on the entire switch, do I? Because what about those trunk ports that go to other switches, right? What about the trunk ports? I don't want to create loops in that environment. So when you use the spanning tree port fast default command, it only enables spanning tree on the ports that are not trunks. All VLANs, all access ports, just any interface that's a trunk, port fast is not enabled. Does that make sense? All right. So there's nothing wrong with using spanning tree port fast default. The only exception to that would be if you had access layer ports that go to other switches. Because just because an interface goes to a switch doesn't mean it's a trunk. It doesn't necessarily have to be a trunk. All right. As a best practice standard, I guess there's nothing wrong with issuing this command, spanning tree port fast default in global mode. Just be aware of the effect of that command. Another option that you have is implementing port fast on a trunk. When would I want to implement port fast on a trunk? Any ideas? I mean, it doesn't sound like something you would ever do, does it? And in what scenarios would that exist? What if I've got a trunk port connected to a VMware server? I mean, ideally, that's not going to cause a loop if I've got a trunk port connected to a VMware server. What if I have a trunk port connected to a router on a stick? Right? So because port fast default doesn't allow the port fast feature to run on trunks, if an interface is a trunk, like we'll just say that interface FA05 is a trunk, I would use the spanning tree port fast trunk command. All right. Spanning tree port fast trunk allows us to enable the port fast feature on the trunk interfaces that I desire to have it configured on. So even though port fast is listed as a configuration option in the security portion of this course, I wouldn't necessarily classify port fast as a security feature. The whole point of port fast is so that we don't have to go through all of the stages of the blocking, listening, learning, and then forwarding stage. All right. So here you see enabling port fast on the interface, and it says port fast has been configured on this interface, but only as long as it's not a trunk. I can issue the command spanning tree port fast trunk if I want to enable port fast on a trunk interface and so on. And lastly, spanning tree port fast default, which allows me to enable port fast globally on the switch. And there you go. All right. Any questions about port fast? Pretty basic concept. All right. Like I said, the most common type of spanning tree attack is to attack the root. Why would that be? Why would my goal in a spanning tree attack be to attack the root? It's not where the traffic flows to, but it's where the spanning tree topology, it's what the spanning tree topology is based on, right? So if I can affect who the root is in the network, I could potentially redirect traffic to different locations. Here's an example. I've got a switch here on the left. The switch on the left has a priority of 8192. And I've got a switch on the right that has some other priority. So this switch on the left, probably 32768 because that's the default. So the switch on the left becomes the root bridge, meaning that if the attacker has two connections to these switches, one of those links is going to be disabled because that would create a loop in the network. It would probably be better drawn here if the attacker was connected to a downstream switch or an upstream switch, okay? But if I can start sending in these things called superior BPDUs, a superior BPDU is simply a BPDU that offers a better choice for the root than whoever the current root is. All of a sudden, the link between the switches stops working. And then what happens? Then all the traffic that flows from switch to switch flows through my PC. Now I can capture all the frames that I need because that traffic is flowing through my PC. We do that by affecting who the root is. So there has to be a mechanism in spanning tree that allows me to protect which switch becomes the root. Of course there is. That's why we're talking about it. And we'll get into that in a second here. All right. One of the options that we have to protect this from happening, one of the options that we have, my switches are a little jacked up here. Let's fix that. Escape, discard. I don't know why my switches are messed up here. One of the mechanisms that we have available to us to protect against rogue devices claiming to be the root is something called BPDU guard. All right? BPDU guard is a very simple feature to implement. You can either implement it globally, as you can see here, using the spanning tree port fast BPDU guard command, or you can enable it on a per interface basis. If you enable BPDU guard globally, it only gets enabled on port fast ports. That's why in the global configuration mode, the configuration command is tied to the port fast command. So spanning tree port fast BPDU guard says any interface that's port fast enabled will have this BPDU guard filter turned on. You guys remember what a BPDU is? Sorry? Well, I mean, you can tell me what it stands for, but I don't really care about that. What it does, what it carries, what it allows to happen, right? First of all, it stands for Bridge Protocol Data Unit. And what it's used for is to identify, it's used by the spanning tree algorithm to identify who's the root, who's not the root. It's how everything gets negotiated. So if I can influence the network by generating these BPDUs, I can cause things to happen that we don't necessarily want to happen. All right. So if I enable BPDU guard on the interface, it's enabled regardless of whether or not that interface is a port fast port. What happens when a port has BPDU guard enabled? Let's go ahead and I'll show you. So interface FA0/4, spanning tree, BPDU guard, enable, And if I take a switch and plug it into that port, I'll just grab any old switch here, and I'm going to plug it into port 4 of the switch I just configured. And you'll notice that the port comes up, all right? But then it says here, so the port status changed to up, right? The line protocol changed to up. Received a BPDU on port 404 with BPDU guard enabled, disabling the port. So the purpose of BPDU guard is to essentially disallow BPDUs from arriving on that port.
Switches that are already connected to each other when they send those BPDUs every 2 seconds.
Yes, so for ports that go to other switches, you would never want to enable this feature on those ports. It would disable those ports, all right? And there's no option here. The only option is to disable the port. If I get a BPDU, shut off the port, period. All right? So this is a protection mechanism that we employ that prevents an attacker from injecting BPDUs into our topology. All switches send BPDUs. Spanning tree runs on all switches. Okay. So as soon as a BPDU gets received on this interface, the port shuts down, which means we've effectively blocked the attacker with the goal of, most likely with the goal of trying to become the root or influencing the root selection from doing so, because we blocked the BPDUs on that interface. Very simple configuration, and you have the option. Enable it globally. It'll be enabled on all my PortFast ports, or enable it on a per interface basis. For me, as a network engineer, when I do my implementations, I use the PortFast feature number 1, and then I use the BPDU guard global configuration command number 2. Because that makes sense, doesn't it? PortFast ports should be host ports. Right, so we're locking down those host ports so that we won't be able to receive BPDUs on those ports. All right. So if we enable BPDU guard, PortFast BPDU guard prevents loops by moving non-trunking ports into an error-disabled state when a BPDU is received on the port. The port doesn't actually recover itself if it's gone into this error-disabled state. In fact, what you have to do is disconnect the switch that's causing the BPDUs and then shut down the port and bring it back up. It's one of those scenarios where the port itself doesn't recover. But there is a error disable recovery cause that we can use to enable the port, and that's BPDU guard. All right. So I can come into my switch, go into global configuration mode, specify error disable recovery cause BPDU guard. I can specify the number of seconds that need to pass before the recovery is enabled or enacted, and then the ports will recover themselves. So if the BPDUs stop after 400 seconds, the port will autocorrect itself. Does that make sense? All right. Another option that you have is to enable a feature called root guard. Now this diagram does describe the root guard feature, but in reality the root guard feature is typically used in a different type of scenario. Oh, Bernard asked a question. How would the attacker inject BPDUs with a PC? Well, there are several applications that do it. The most common that everybody tends to use is Yersinia. Yersinia actually has a feature built into it to generate BPDUs.
I mean, any network controller can generate any packet.
Any frame, yeah.
Any frame it
Doesn't
wants,
matter.
Any frame
Right.
it wants. You just have to know how to form it and send it.
Yeah, and you can actually do it yourself in command line. There are packet generation tools and frame generation tools that allow, because it's just ones and zeros, right? So you create a script and says, okay, here's the first block of 48 bits, here's the second block of 48 bits, and then the interface will start streaming that information. That's all these tools do anyway. They're just generating raw data. They don't understand what the data represents. It's just formatted a certain way so it looks like something. Okay. The root guard feature is typically used more in this type of scenario. Actually, let me check and see. Yeah, they don't have a diagram of that here. So let me draw really kind of a better diagram to represent when the root guard feature would be used. So I've got this switch, I've got this switch, some sort of ether channel configuration there, bonding the links together, and then I've got my access layer switches that go to the distribution layer. So this is D2, this is D1. Those are my distribution layer switches. This is my access layer 1, access layer 2. Pretty typical topology, to pretty typical design. Provides redundancy up to the distribution layer. If one distribution layer switch, the other one takes over. Naturally, these are the switches that you would want to be the roots in your spanning tree topology, not your access layer switches. So root guard is a feature that I would enable on this interface, this interface, this interface, and this interface. Just keep that in mind as we go through the discussion of what root guard does. All right. So it is an interface specific command. It's a configuration that we do directly on the interface. And essentially what it does is it says, hey, if I put root guard on these two interfaces and I start getting BPDUs that are superior than my root, then those ports error disable. They actually go into something called a port inconsistent state, spanning tree inconsistent, which means they're unusable. But unlike BPDU guard, if the superior BPDUs stop, then the ports start operating again like normal ports. All right?
So it's blocking more traffic, but it's watching more traffic.
Yes, it's still monitoring for BPDUs. What's going on here? It's still monitoring for BPDUs, but it is blocking frames, host frames, right?
And does it inconsistent?
Go ahead.
Does inconsistent ports show you all error disabled ports? Not just
No,
the ones-
only the ones related to this feature.
Okay.
Not only, yeah, actually it's directly related to this particular feature. Right? Inconsistent ports related to this feature.
Oh, because they come back up right after that.
Right. They become, if they stop getting the superior BPDUs, they become consistent again.
So you have a tightly locked down office. Some guy comes in with a switch because he wants to add a couple of devices in his office. This thing is on. They'll plug it in and all of a sudden this network won't be working because nothing connected to the switch is getting through. Right, because the switch is sending BDU ports.
Yes.
Yes.
I know.
BPDU.
BPDU. Say it 10 times fast.
And then he takes it off, and all of a sudden things start working, and he scratches his head, and then comes into IT and explains to us, we take the switch right there.
Right. Yeah. And then you put them up against the wall and you start flogging them. Yeah. Okay. Now there are other spanning tree protection mechanisms. There's ether channel guard. There is a loop guard. There are many other spanning tree protection mechanisms, but our primary goal in the case of protecting spanning tree is to protect against somebody from claiming to be the root. For either the purpose of changing or influencing the topology of our network or for the purpose of capturing frames so that we can analyze those frames or modify them or do whatever we want to do with those particular frames. All right. Another protocol that is highly susceptible to attack, it's in the layer 2 security chapter. It really shouldn't be. DHCP is an application layer protocol, but is to protect against DHCP attacks. DHCP is a client-server broadcast-based model. Obviously, we know what DHCP does. It allows us to assign IP addresses, subnet masks, gateways, etc. to our clients through a dynamic process. But because the process is broadcast-based, it's susceptible to attack and it's vulnerable to attack, right? DHCP servers allocate network address information to their clients and to their destinations or to the requesters in the network, okay? And the DHCP client gets that information from the DHCP server. We call this the DORA process because it starts with a DHCP discover, which again is a broadcast for, it's a client essentially going out and saying, hey, I need to get IP address information. Is there anybody out there that can provide that information to me? Then we have a DHCP offer, which comes from the server. We talked about this in the CCNA class. And then we have the request, which then comes from the client saying, I like what you have to offer. Can you go ahead and assign me that information? And then I finish up my discussion or my transactions with an acknowledgement from the server saying, this lease is now active. Go ahead and use the address. Because DHCP is broadcast-based, it is possible to have rogue DHCP servers in the network responding to the discovers with invalid offer information. All right. So what would be the purpose or the goal of poisoning DHCP information? We talked about this previously, right? The goal is to say, to either insert invalid configuration parameters, like here's your DNS server, but the DNS server is actually one of my servers that I control, or here's your default gateway. So a DHCP spoofing attack is essentially a rogue DHCP server. All right. Client sends a discover. The attacker is the one that sends the offer. The client accepts the legitimate request, and the attacker responds with the acknowledgement. And now we have effectively an infected host that has invalid DHCP information. In order for this attack to be successful, the rogue server would have to reply to the offer before the legitimate server would reply. Because once an address has been leased, even if I send out an offer, the client rejects that or doesn't accept that offer because that offer was already received. Another offer was already received by the client prior to the one that the attacker sent. All right. Another type of attack against DHCP is what we call a DHCP starvation attack, where I send a bunch of flooded DHCP requests in with spoofed addresses, and the goal is to have the DHCP server allocate all of its address space to these rogue DHCP messages. You might look at this and go, well, we can protect against that by using port security. Well, why is that not the case? First of all, how does DHCP map its lease assignments to the client? What is DHCP tracking in order to provide that mapping? The MAC address. Well, the IP is what's being assigned, but the MAC address is how we identify that. So if the client starts generating a bunch of DHCP discovers with different MAC addresses, then the server starts issuing IP addresses to each of those spoofed MAC addresses.
Well, the Would you have to send an acknowledgement that says, okay, I accept these addresses for it to go on?
Sure, but why wouldn't you be able to? If you're already spoofing the MAC addresses to send the Discover, why wouldn't you be able to send those acknowledgments as well? Well, it would be a request, not an acknowledgement. A request comes from the client. The acknowledgement comes from the server. It will not. Thank you for saying that, though, by the way. Port security does not protect you against this type of an attack. Why not? Anybody have any idea?
Oh, because it's like, it's within the frame, the MAC address is not.
DHCP operates at the application layer, and it's within the DHCP payload data is where the MAC address is referenced. The frame, the MAC address of the frame doesn't have to match the MAC address of the request. Right? We're not spoofing a MAC. We're rewriting the payload information with alternate MAC addresses. So port security wouldn't actually protect against this type of attack. It kind of makes sense if you think about it, because DHCP servers can be in different subnets. And layer 2 information doesn't go through a router. So it's not that layer 2 information that allows me to allocate addresses. It's the layer 2 information that's within the DHCP header. Or not the header, the DHCP payload. All right. In fact, let me pull that up real quick. You look at a DHCP packet in Wireshark, and you look at the payload information, right? This is a DHCP request, which is which type of message? It's not the initial message. It's not the discover. It's the third message, which is the second client to server message, which is the request. And of course, it doesn't show what I want to show you. After I set all that, it doesn't actually provide the information that I was looking for. I should just go ahead and do a Wireshark capture. Here we go. All right. So you can see that the MAC address in the frame itself, well, again, we don't have the frame here. The MAC address within the frame itself, let's just do a capture so we can actually see it. All right, for those on the WebEx, I might lose you for a second as I do my IP config release and renew. So I apologize in advance. top to the top. All right. Well, tell me I didn't capture. Oh, there we go. All right. So there's the discover, there's the offer, there's the request, there's the acknowledgement. The 4 stages of DHCP. If I go into my discover, the MAC address here in the frame header, the source MAC address here does match the MAC address in the actual discover, the client MAC address here, 02C734. But my point was this MAC address in the frame does not have to match the MAC address in the DHCP payload. So if I'm trying to flood a DHCP server with requests, I don't even have to change my frame header. All I have to do is change the MAC address represented in the DHCP scope, in the DHCP configuration. All right. So something to consider when you're looking at DHCP. All right. So, how do we protect against that? We use something called DHCP snooping that also works in conjunction with dynamic ARP inspection. All right, because ARP is also another protocol that we have to protect. And we'll take a look at the configuration of that as we move through the chapter here. In fact, here's the first part of that. Whoops, what happened? Oh no. Took me all the way to the end of the slide. Hold on. Sorry about that, guys. How dare me. Which is DHCP snooping. All right. If a client sends, I've got a question online. If a client sends a DHCP discover on a subnet with several DHCP servers, how do we determine which DHCP server responds first? You don't. Right. Does this behavior, is it tunable in the DHCP server? Yes, and that's essentially how it works. If you want to ensure that a particular DHCP server is the one that is primarily responsible for defining or sending out leases, then we would make sure that that server responds before all the other servers. And so there's a delay function that you can configure in your DHCP server to delay DHCP messages from being sent out the network. Okay? So what DHCP snooping does, and this is something that we would configure on our switches, is it allows the administrator to identify where certain types of DHCP messages are allowed to come from. Trusted DHCP ports, trusted DHCP ports are allowed to source all types of DHCP messages, whereas untrusted DHCP ports are only allowed to source or allowed to pass discovers and requests. Why specifically discovers and requests? Those are valid client messages, not server messages. All right, so I've got my legitimate DHCP server here. I've got a client here, and I've got my attacker here. If I've configured DHCP snooping on these two switches here, and I made these untrusted ports, and of course my uplinks would have to be trusted because they're going to be passing server messages. As soon as the client sends in an offer or a request, an offer or an acknowledgement, that traffic is going to be filtered at the interface level. So essentially, an untrusted interface is only allowed to source or allow inbound client-based messages, like a discover and a request.
Which can
Well, you acknowledge the acknowledgement comes from the server to the client, not from,
Oh, right, right.
you know, so we're not necessarily protecting against starvation attacks here. Our goal here is to protect against spoofing attacks. That's what our goal is. We're trying to protect against spoofing attacks. Now, there is something else that DHCP snooping does. It builds a database in Flash called the DHCP snooping binding database, where it maps the client's MAC address to the IP address that was assigned, to the VLAN, to the port, which, by the way, can then be used to prevent IP spoofing attacks. Because if I've monitored this DHCP process from the client side, the client sends in a discover, so I make note of the client's MAC address. I get the offer going out the port, so I make note of the offer. And I get the request and I get the acknowledgement. So now I've identified that this IP address with this MAC, with this port, well, is on this particular port.
Is that a default behavior?
What do you mean?
The DHCP?
Snooping? No, it's not turned on by default.
What about on multi-layer switches that distribute?
Not a lot. Excuse me, not turned on by default. This is something that you have to configure. Now, the one thing that allows us to protect against starvation attacks is the ability to also rate limit the amount of DHCP traffic that's allowed on an interface. So rate limiting is something that we can do in conjunction with the configuration of DHCP snooping. All right. DHCP snooping is enabled on a per VLAN basis. By default, the feature is not active on any VLAN. You can enable this on a single VLAN, or you can enable it across multiple VLANs. It's enabled in the route processor, so all of my DHCP messages for the VLAN are intercepted by the PFC and then directed to the route processor for processing. Rate limiting untrusted ports to packets per second. Cisco recommends 100 packets per second, so that we don't exceed the amount of packets that would potentially cause a starvation attack. I honestly don't know where they got the 100 packets per second. For me, that seems kind of high. Because we're not talking about any packets. We're talking about packets specific to DHCP. Here's the configuration. Really simple. Global command IP DHCP snooping enables the feature. And then we turn it on a VLAN. So on the second command here, we're enabling DHCP snooping for VLAN 2. Very important concept I'm about to tell you. When you enable DHCP snooping on a VLAN, automatically every single interface in that VLAN now becomes untrusted. So be very careful. You don't want to implement this in the middle of a production day because your DHCP services will be unavailable as you're configuring it. That makes sense? When you enable the DHCP snooping feature, every port becomes untrusted by default.
When you say every port, you refer to the entire switch or every port?
Every port within the VLAN on that entire switch. All right?
Which wouldn't affect those posts attached, but you had uplinks.
Uplinks, or a server happen to be connected to that switch directly. Right. Now, it would only affect you as much as if somebody's actually doing a DHCP discover at the time you implement the configuration. Obviously, you're going to have some trusted ports, whether they're the uplink ports that go to your data center where your DHCP server is connected, or whether it's a a backbone port, or it's a port connected directly to a DHCP server on that switch. To trust a DHCP port, in other words, to allow it to source server-based traffic, we just use the command IP DHCP snooping trust. And then we can do our rate limiting using the IP DHCP snooping limit rate command. And again, that number's in packets per second. So if I go in here and I type in show IP DHCP snooping, port 10 and port 1 are configured for snooping. Port 10 is not trusted. Port 1 is trusted. And port 10 is limited to 100 packets per second.
So it's still able to send DHCP requests, it's just limited in the amount it can?
Yes. The number of packets or number of requests per second is limited.
So you're not necessarily disabling, so like you're saying disabling production. If there were less than 100 packets per second sent, then technically you wouldn't.
No, that's not true. Because remember, there's a difference between what type of traffic a trusted port can pass versus what type of traffic an untrusted port can pass. Untrusted ports are not allowed to receive, I should say, DHCP offers or acknowledgements. So if my DHCP server is connected to port 10 and I enable this snooping feature, port 10 can no longer accept offers or acknowledgements, which means that clients can't get addresses. So you have to make sure the ports that go to your server or have an uplink to a data center or whatever it might be that's in your network, you need to make sure that you have those ports listed as trusted. All right. Yes. They would show up as untrusted, right. They may not have the rate limiting configuration applied, but they'd still show up as untrusted. And remember, an untrusted port is still a normal Ethernet port. It's still passing normal frames. The only difference is, and it can even pass DHCP data, the only difference is it can't pass offers and acknowledgements. All right. ARP, another protocol that's highly susceptible to attacks in the network because of its dynamic nature, needs to be protected as well. Fred on the left wants to talk to Barney on the right. We know what the purpose of ARP is. Fred knows the IP address of Barney, but before Fred can build his entire PDU, he has to go out and discover the MAC address of Barney. That is ARP in a nutshell. But it is broadcast-based, so it is susceptible to attack. All right? An ARP poisoning attack is simply where somebody sends a gratuitous ARP or replies on behalf of somebody else's ARP request to say, this is my MAC address. Here's an example. Host A wants to talk to his gateway for the first time. The gateway is 10.0.1.1. Naturally, host A is going to go ahead and send out an ARP request to identify what the MAC address is of the router. All right? What the MAC address is of the router. The router is going to respond because it definitely got the ARP request, so it's going to respond with its MAC address. Now, in the whole process, host B saw that request and says, okay, I'm going to wait for that router to respond, and then I'm going to respond again, but this time I'm going to use the MAC address of my ID or my interface in that response. The goal, obviously, is to get host A to think that I am 10.0.1.1. And there's really no way to protect against this from happening. There's really no way to protect against this from happening. I should say that with the caveat, of course, in a normal operation, a normal switch operation. In other words, a switch that has its default configuration. All right. Unless you're running something called dynamic ARP inspection. Yay. DAI, dynamic ARP inspection, validates the ARP requests and the responses and drops the frames that don't meet the criteria set forth in the dynamic ARP inspection protocol. So when you enable dynamic ARP inspection on your switches, they're going to intercept all ARP messages, and then they're going to compare those requests to information they have stored. And if the requests or the replies or whatever it might be doesn't match the information I have stored, then I drop the information. I drop the frame. All right? You might ask yourself, well, how does the switch know what's valid? Dynamic ARP inspection works in conjunction with DHCP snooping. In fact, you can't configure dynamic ARP inspection unless you have DHCP snooping configured as well. All right. Here's how it works. I've got a client connected to this network. All right. And let's say that client plugs into the network. The first thing typically that client is going to do is going to be doing a DHCP discover. Agreed? So it's going to send out a DHCP discover. It's going to be assigned an address from the DHCP server. But with DHCP snooping, the switch is building a database of that transaction. It's saying, okay, the MAC address of the client is X. The port the client came in on is Y. The address that the DHCP server assigned to the client is Z. So if the rogue device here sends in an ARP reply, and again, DHCP snooping would be running on this switch as well, the attacker sends in a poisoned ARP reply, the switch compares where the ARP came from, what port it came in on, what subnet it was on, and it says, you know what, you're not on the right subnet, you're not in the right port, you're not even the right MAC address. So I'm not going to allow that traffic to pass. Well, this is a feature you would configure on all your switches.
How does each switch know about the other switches?
It doesn't need to. Okay? Because the rogue attacker, in order for him to be able to do anything bad on the network, he's going to have to get a DHCP address as well. Right. If he statically assigns himself an address, he will not be able to communicate because there's no binding in the DHCP database, which has to be there. The binding table is always monitored. If I give myself a static address, I don't have an entry in the binding table. And by default, I'm blocked from communicating because I don't have an entry in the binding table. Make sense? We actually have another slide that describes this process in a little bit more detail. All right. All right. So here we go. Client on the right. Now we've got two things configured on this switch. We've got dynamic ARP inspection configured, and we have DHCP snooping configured. So when this client booted up initially, it sent out a DHCP discover. Because this port is untrusted, it's only allowed to receive a discover and receive a request, because those are the only two client message types that are allowed. But because the discover is allowed, this PC gets an offer out the port. Now the switch is monitoring that whole transaction. It knows the MAC address of the client through the discover process, and it monitors what was offered to the client through the DHCP process. The client then sends a request, and then I send an acknowledgement. So by the time that entire transaction is done, the client's IP address, the client's MAC address, the client's port number, they're all mapped, and VLAN ID, they're all mapped to that in that database. So if I send in a ARP request, well, let's say I'm going out to the internet, right? So I'm going to 10.0.1.1. I'm going to send an ARP request to my gateway. The gateway is going to respond. And again, the switch starts learning about that gateway. It learns what port it's on, what MAC address it is, what IP address it is, etc. And it's going to map that information to that port as well. Conversely, if the attacker tries to poison that information by telling the gateway or the 10.0.1.2 host that the MAC address for 10.0.1.1 is my MAC address, the switch goes and compares the information received on that interface with the information that's in the database. It doesn't match. What happens to that frame? It gets discarded. All right. How do I configure dynamic ARP inspection? You just enable it on the VLAN, just like DHCP snooping. IP ARP inspection, VLAN 2. By default, when you turn on dynamic ARP inspection, all of the interfaces are untrusted. Which interfaces do you think I want to make trusted?
The same ones that you do with DHCP stickers.
Servers, routers, devices that might not be running DHCP. I'll make those just automatically trusted. Those ports anyway.
So it won't affect the acknowledgements or anything like that.
Right. And you, because you're not running DHCP on those devices typically, even if the port was running snooping, which it does because it's enabled on the VLAN, I'm not going to capture any information because I'm not going to see any DHCP information. Does that make sense? All right. So that is the end of that chapter.